Hey guys, I'm Avilash Ravi from VID Chennai. I shall be delivering a comprehensive presentation on the software application known as NAND2TETRIS, which is a hardware simulator application. So this presentation is part of a digital assignment which is an integral component of my fall inter-semester 2023 curriculum encompassing the field of operating systems. So come on, let's get started. So let's discuss the contents that we'll be covering in this presentation. Firstly, we'll be starting with the installation of the simulator. I'll be showing a hands-on demo on how to install the software and how to use the hardware simulator. Moving on, we'll have an overview of what this software is about, what can be done and what can be achieved using this software. And third step is the logic gates. I'll be elaborating on the various kinds of logic gates such as the AND gate, OR gate, NOT gate, etc. using the universal NAND gate. We will be informing all kinds of combination of gates. We'll also have the multiplexer and the demultiplexer as well covered in this presentation. And last but not the least, we'll end with a good conclusion on what we have learned in this presentation as well. So now let us take a look at the installation steps in order to install this NAND2TETRIS software. So first we have to go to the site nand2tetris.org/software, and we have to go down to the software suite section, and we have to download the zip file that will be available there, unzip it, and based on your OS version, whether it's Windows, Mac or Linux, we have to follow the commands as per the slides which I have written. And once we have done all these processes, we have to double click on the hardware simulator file or CPU emulator on Mac, or we have to run the chmod +x hardware simulator.sh option in Linux OS. Based on your software, based on the operating system that you're working on, these are all the steps you have to go through. And once after that, we have to just go on to the projects folder and take the required project and run it in the hardware simulator. Now let me just show you a hands-on demo on how this process is done. So now let's go on to the installation part for NAND2TETRIS. Just go to your browser and type NAND2TETRIS. You will get the first link and go on to the software section. Download NAND2TETRIS software suite. Click on download. So you will get the zip file that will be downloaded here. Now go to downloads. Just extract the folder that has been downloaded. So extract. It will take some time, but it will be downloaded. So almost done. So yes, so 100% has been completed. Now we have the folder here. Just click on NAND2TETRIS and you have two folders here. Click on projects. So you have all the project folders here, and just click on project 1. You have CMP file as well as HTL file and TST file as well, but we will be using these two, which are the script file and the VHDL file, and DMux, MUX, and all the different gates are there in this folder. Go to NAND2TETRIS folder again and go to tools this time, and you will be finding the hardware simulator batch file. Just click on that, and yep, you get the graphical user interface that I had mentioned earlier, and you have see the slow and fast options. You can adjust that like based on your wish and convenience. So that's that, and you have the area to import your HDL files and your script files. And once you are able to open this hardware simulator, we are good to go. Now let's move on to the slides. So moving on to the overview slide. So NAND2TETRIS software is an educational software project that allows you to build a complete computer system from ground up, from scratch basically. It was initially developed by Noam, Nissim and Shimon Shokin as a way to teach students on computer architecture and development. So the hardware construction part is where you start with just a single component, a NAND gate, the universal gate, and gradually build up to a fully functional computer including a CPU and memory. NAND2TETRIS provides a hands-on approach to learning computer science and the way you understand how hardware and software work together. It's basically providing a link on how the hardware and the software coordinate and work hand in hand and make a complete computer. So this slide explains about NAND2TETRIS as two entities, hardware and software. In the software development part, focuses on writing low-level software including an assembler, a virtual machine, and high-level programming language called Jack. In the hardware construction part, you start with just a single component, the NAND gate, the universal gate, and gradually build up a CPU and memory and making development in computer architecture. Moving on. So let's take a look on the software hierarchy part in this slide. So first step is the human thought. What is the human thought? The logic that we develop for a particular algorithm or the aim which we have to achieve using the program. So we just write a program. What does the program what happens to the program after compilation? It gets converted into high level language. The high level language using the process of abstraction gets converted into a VM code using a VM translator. Now this VM code is in turn converted into low level language using the assembler. When converted into low level language or machine understandable code, it's passed on to the hardware platform. So this is the process to put it in a nutshell. So what are high level languages basically? High level languages are basically nothing but the Python, Java or the script that we write in modern day software development scenarios. And low level language or machine understandable code is nothing but the assembly language program that we write for hardware, especially the microprocessors, chips and controllers, etc. So now let's move on to the hardware part. So yeah, coming to the hardware platform, first we will look at the computer architecture that we require for our logic, then the digital design which includes CPU, RAM and chipset, then the gate logic that we have to design for our logic. The logic which we devised can be achieved using different gate logics or combination of gates. So this can be achieved by using the elementary logic gates based on our requirements. And last but not the least, the electrical engineering part is where we manufacture the board or the chips based on the logic that we have devised and implement them in real life scenarios. Moving on. So let's move on to the basics of digital logic gates. Digital logic gates are fundamental building blocks of digital circuits. Logic gates perform logical operations on one or more binary inputs to produce a binary output. So the most common logic gates are the AND gate, OR gate and the NOT gate. Other logic gates include the NAND, NOR, XOR, XNOR gates, which are derived from combinations of other basic gates as well. But this gate, the NAND gate, as the name suggests, NAND2TETRIS, the NAND gate is a universal gate. Using the NAND gate, we can devise all the possible AND, OR, NOT, XOR, and every combination of gates can be made using the NAND gate, which I will be elaborating more on the upcoming slides. Moving on. So yeah, let's start with the basic AND gate. So the AND gate is a fundamental logic gate that takes two inputs and produces an output based on their logical conjunction. So if we look at the truth table, it will be more understandable for us. So if you have a single input of 0, as you can see, we get 0 as the output. And if we have both our inputs as 1, we have the output as 1. So this can be implemented using the universal NAND gate. As you can see in the circuit diagram that I have attached, we have two NAND gates, one NAND gate for the input and one that takes the output from the first NAND gate as inputs to the to it and gives the output as AND. So basically this circuit just represents an AND gate, and now we are just implementing this circuit as code in VHDL. I think after the circuit, the code will be just self-explanatory. As you can see, the first line, NAND A is equal to A, B is equal to B, and out is equal to NAND output. So that's the first output, that is this part. And we are taking that output in both A and B of the second NAND gate and producing an output. This output is nothing but AND. So that makes the AND gate. Let's move on to the next gate. Now let's go on to the OR gate, the next fundamental gate. The OR gate is another essential logic gate that takes two inputs and produces an output based on their logical disjunction. So that's the definition for OR gate. So now let's see the circuit diagram, how to develop an OR gate using the NAND gates. So we use 1, 2 and 3 NAND gates in order to get or develop an OR output. Let's take a look at the truth table as well. When one of the inputs is 1, we get the output as 1. If both the inputs are 0, then the output is 0. So that's the logic behind the OR gate. So to implement this, we require 3 NAND gates as previously seen in the diagram, and the code is self-explanatory as well. The first output of the first NAND gate and the second output of the second NAND gate are again passed on to a third NAND gate, which in turn gives the OR logic output. So we'll be also demonstrating this in NAND2TETRIS software towards the end of the presentation. Let's move on to the next logic gate. So the NOT gate. So NOT gate is actually very simple as compared to AND and OR gates. The NOT gate is also known as an inverter, which takes a single input and produces a logical complement of the input as an output. So as you can see the truth table, for 0 it should produce 1, and for 1 it should produce 0. Okay, so now let's take a look at the circuit diagram. As you can see, there is a single NAND gate, and in the NAND gate we are giving a single output, that is A and B both are equal. So now that we are just implementing the same in code, A as input and B as input with the same variables. The output will be the inverted value, of course. So that's why we are getting 0 for 1 and 1 for 0. So that's a simple NOT gate implementation using the NAND gate circuit diagram and VHDL code. Let's move on to the next gate. Now coming to the XOR gate. The XOR gate or exclusive OR gate produces a true output only when the number of true inputs are odd. Okay, now let's look at the truth table. When the inputs are same, that is in case of 0 and 0 and 1 and 1, it produces an output 0. But when the inputs are different, it produces 1. So that's the truth table, which is explanatory. Now how can we implement this using the NAND gates? So there are 4 NAND gates here. 1, 2, 3, 4. So there are 4 NAND gates here. And I think using the circuit diagram, we can just implement it as the VHDL code. Since there are 4 NAND gates, we are using 4 NAND functions. With that self-explanatory for you. And the input of first A goes to the second NAND gate and to the first NAND gate respectively. So that's this part. And B input goes to the third NAND gate and the first as well. So that's this part. And the outputs of 2 and 3 goes to the fourth NAND gate. That's what you can see here. 2 and 3 outputs goes as inputs to the third NAND gate, sorry, the fourth NAND gate, and finally we get the output as XOR output. So this VHDL code we will be implementing using the script and VHDL command in NAND2TETRIS, which I will do after elaborating on the presentation slides as demonstration. Moving on next to multiplexer. So coming to mux or multiplexer, a mux or multiplexer is a combinational circuit that selects one or more inputs and forwards it into a single output based on a select signal. A common example of a 2:1 mux is that it has two data inputs and one select input and one output. The output of a 2:1 mux is determined by the select input, which chooses between the two inputs. I think looking at the truth table and the circuit diagram, we can figure out the VHDL code that has to be implemented in NAND2TETRIS. So since it has two AND gates and one OR gate and an OR gate, as you can see, we have four parameters here that has an OR gate, two AND gates and OR gate. So based on the connections, we are just giving the parameters here like input select and not select, and based on the let's take this part for example. We need the output of the first AND gate and the second AND gate in the OR gate. So in the OR gate we have AND1 and AND2, and finally we get the output, which is the mux output. So basically this will be outputted by the NAND2TETRIS software. So moving on to DMux. Now coming to DMux, it's also similar to mux. A DMux or demultiplexer is a combinational circuit that takes a single input and distributes it to many of inputs based on the select signal. A common example of the 1:2 DMux is shown as circuit below. So this circuit is what we have to implement in VHDL as code. So it has one NOT gate and two AND gates, 1 and 2. So yeah, we have the same NOT and two AND gates implemented as code here, and based on their inputs and outputs we have to just give parameters under the parts function as part of the demux in VHDL code. And as you can see, while we implement this logic here, we will get the output as these based on the truth table. Moving on, let's go to the next slide. So the most awaited part of this presentation is the demonstration that I will be doing using the NAND2TETRIS software. So before going to the demonstration part, I want to make a few certain points clear. So first, what we did was we used a NAND gate. We created three basic gates, that is AND, OR and NOT. So this NAND gate, using the NAND gate, we were able to produce these three gates. Now using these three gates, we were able to produce the mux and demux configurations. So we will be implementing all these concepts using the NAND2TETRIS software. Also, we will also be modifying the number of input lines. For example, AND 16, AND 8 inputs and 16 inputs, like that. We'll modify the number of inputs and also give the simulator software a try as well. So let's move on to the demonstration part. So before the demonstration, I would like to make a few clarification on the steps to execute a program in NAND2TETRIS. First, we have to successfully install the NAND2TETRIS software suite on the computer, and we have to locate the hardware simulator file that is present in the extracted folder of the NAND2TETRIS for software. Then we have to double click on the hardware simulator file to launch the hardware simulator. Once the hardware simulator is open, you will see a graphical user interface with various options and buttons. To load a hardware project or circuit, click on the load button in the GUI. This will open a file dialog where you can navigate to the project and select appropriate hardware description files such as AND gate, OR gate, or pre-existing files which will be stored in this folder itself, which you will have access to. And for our project, since it's project 1, it will be present in project 1 folder of the extracted NAND2TETRIS file. Then after loading the hardware description file, we have to also load the script, that is the VHDL code, which I have explained in the PPT right now as well. so that we'll get the outputs or the truth table that we seek to get based on the logic gates that we opt. To run the simulation, click on the run button and GUI. Also, we have three modes: the slow, medium, and fast modes. Based on your wish, you can execute in slow mode or the fast mode for faster results and slower results respectively. You can observe the changes in the output values as you toggle the input values as the circuit process based on the inputs provided in the VHDL file. By following the steps, we'll be able to simulate hardware circuits using the hardware simulator in NAND2TETRIS. Now let's move on to the hands-on session. So now let's move on to the demonstration part of this NAND2TETRIS tool. Now let us load the chip file and the AND file chip. Load chip. So once we load the file, we get the AND logic that I explained in the presentation slides using the NAND gate. Now let's load the script file and.txt load script. So as you can see in this load, the first statement is and.hdl. And.hdl is it's like import statement. We are importing the and.hdl, that is the chip file. Then our output file as and.out they are declaring, and we have to compare to and.cmp. And.cmp is nothing but the compare file. This compare file I can show you here. One second. So go to NAND2TETRIS, go to the folder, go to projects, go to 01, and yeah, just yeah, this is and.cmp file. Just open it with notepad. Now you can get a clear idea of what is the cmp file. Open with notepad. Yeah, so what does the AND gate do? For both the input as 1, it should return 1, and for the rest it should return 0. So this is the required output for us. So we need to get the same output when we execute it in and.out file. So what we will do is, let's go here. Now we have to execute it. So since we have loaded the HDL file as well as the script file, now let's execute this file. So these steps are nothing but setting A0, B0, A0, B1. These are all the truth table, that is 0, 0, 0, 1, 1, 0, 1, 1 and 1, 1, and the output values for the respective inputs. Now let's go to the output. As you can see in the output, we get 0, 0, 0, 0, 1, 0 and 1, 0, 1, 1, 0, 0 and 1, 1, 1. So the logic is AND gate. So AND gate truth table is generated. Now we have to compare. Once we compare, we get the same input, correct? So that's the AND logic. Now let's go on to the OR logic. Sorry, now let's check out with AND 16 now. Load the script file. So this is the script file. As I said, since there will be 16 inputs in this case, we are given 16-bit inputs in the program, and the AND 16 logic in HDL chip is also given here under the HDL loading interface. Now let's see the output. First let us execute. See, when we generate the output, we don't have any output because we haven't run the code yet. Now let's run it. Once we run, as you can see, it generates the output for us, A, B and output, and its respective output following AND 16 logic. So that was AND 16 gate. Now let us load the next chip, that is DMux. Load chip. So DMux chip is loaded. Now let's load the script for DMux. Demux.txt load script. Script is also loaded. So again they have set the logic here. Now let's go to the compare section. Compare is also not there. Okay, so we have to first run it, right? So now let's run this code. So as you can see, as I explained earlier in the presentation, these are the logic for DMux chips. So by adhering to the logic, the truth table is generated, and as we can see, for each select value and input, we are getting A and B values respectively. for the Demux. Now let's go for Demux 4-way load chip. Chip is loaded. Here Demux 4-way, they have declared the logic here. As you can see, as I explained for Demux 2:1 as well. Now let's choose the script file. Load script. So script is also loaded, and they have given for every input values and output values. Now let's run the code. Okay, this code is run. Now let's check the output. Yeah, there you go. There you get the output. This is the output for Demux 4-way. Now let's continue with the 8-way as well. Demux 8-way load chip. So Demux 8-way chip has been loaded, and let's load the script as well. Everything they have provided in that NAND2TETRIS folder itself. The only thing is we have to know how to execute this in the hardware simulator. So that's the part I am demonstrating right now. So as you can see, as I told you earlier, all the input values have been given, and respective output would be generated. Go to the output and just give run. It will generate the output based on the logic on the HDL chip that we have written here. So there you can see this is the output for Demux 8-way. As I showed you earlier, in the compare file we can compare it and see the compare file also has the same output as that of the output file. Now moving on. Now on to Mux file. Let's load the chip of Mux. Okay, load chip. Go to the script file as well. Load the script. Now just make it fast to save some time. Now keep it in output phase and just generate the output. As I had explained in the presentation, this is the logic for a multiplexer, and as you can see, a table has been generated. Now let's compare the table with the Mux. This is the Mux compare file that is present in NAND2TETRIS folder, and just keep it side by side and compare. You can see that there are 4 zeros, 4, 1, 1, and for the respective select and inputs, the out is 3 zeros, 1, 1, 0, 1, 1. So the output is perfectly matching with the compare file. This we can view manually like this, or else we can also view the compare file here as well. So it's both the same, so the output is correct. Now let's move on to the next Mux configuration. 16-way load chip. Load the script as well. Yeah, so now go to the output terminal, generate. So as you can see, a 16-way Mux has been generated, and here is the logic in the VHDL, and let's see the compare file as well. It's going to be the same. Okay, now let's move on to the next configuration. 8-way Mux load chip. Go to the script file, load the script, and now go to your output and just run the program. Yeah, so 8-way 16-bit Mux is also generated here. As you can see, the output has been printed in the terminal. Now let's compare it. It's the same, so the output is correct. Now let's go to the next configuration, the NOT gate. So come on, let's see the simplest NOT gate here. So as I said in the presentation, we have A and B having the same input and one out. Now load the NOT script. Script is also loaded, and HDL chip is also loaded, and now let's run the program. Before running, let's go to the output. Output is empty. Now let's run the program. As you can see, for 0 it gives 1 and 1 it gives 0. So it's basically an inversion. So NOT gate is also working properly. Now let's go to the next gate, NOT 16-bit. Okay, now load that chip. Load the script for it as well. Go to the output and run the file. So as you can see, for each of the 16-bit values, you get the inverted output. Just observe, and you can also compare it and see and check it. It's the same. So 0 0 1 1, all ones, all zeros, 2 zeros, 2 ones, 2 ones, 2 zeros, 4 zeros, 4 ones, and 2 ones, 0 0. As you can see, for every input the output is inverted. So the logic is also here for the not 16-bit, as I mentioned, for for a sample NOT gate as well. So this is for 16-bit. So for all possibilities they have given the logic here in Verilog HDL chip coding. Now let's go to the next gate, or load the chip, load the script file as well. Now go to the output and generate. Boom, and that's the output. So as you can see, just compare 0, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 1. So for both the inputs, if it is 0, then only we have the output as 0. So OR logic is also correct. We can also compare it and check as well. Compare file is also going to be the same, and this is the logic for the OR gate as I had mentioned in this slide. Now let's go to OR 8-way OR, load chip, 8-way OR script, load it also, go to output, run it again. So for every 8-bit output we are getting the input, we are getting the output here. And the logic here, what they are doing is they are exploring all the possibilities using the truth table. So that is the major logic they have written here. So based on this logic, we are getting the output that has been generated here. So this is 8-way OR. Now let's go to the OR 16-bit load chip and OR 16-bit load script. Go to the output and generate. So here every 16-bit for every 16-bit input we get an output in 16-bit performing the OR operation. As I mentioned earlier, here they have done the logic for all possibilities of the HDL chip. So that is OR 16 for you. And moving on to XOR, last chip, load the XOR chip and load the XOR script as well, generate. So it's generated. Just let's check the output. As you can see, for every same input we'll have 0, and for every different input it will be 1. So as we saw in the truth table from the PowerPoint, it's matching the same. We can also compare it and check. It's going to be the same. Okay, so that's the demonstration, and here is the logic part for the XOR chip as well. As I had mentioned earlier in the presentation, along with the circuit diagram, by a combination of NOT and an OR gates, we will be able to replicate an XOR gate HDL logic. So this is the demonstration part for the logic gates. Now let's move on to the conclusion. So in conclusion of this presentation, we have explored NAND2TETRIS software and demonstrated the implementation of various logic gates used in it. And we have also explored how to use the hardware simulator in NAND2TETRIS, and I have also demonstrated how we can implement the AND, OR, NOT, NAND and XOR XNOR gates, showing how they can be constructed using the NAND gate as well. We have also demonstrated the implementation of MUX, Demultiplexer and other circuits using NAND2TETRIS. Through this presentation, we gained an understanding of how logic gates and multiplexers are essential components in building complex digital systems. By utilizing NAND2TETRIS software, we can develop a solid foundation in computer science and gain valuable insights into inner workings of computers. So thank you guys. Thanks for tuning into this video and presentation on NAND2TETRIS and completion of logic gates. We hope it has been an informative, inspiring, and encouraging session for the fascinating world of computer architecture and further. Thanks guys, thanks for tuning into the video. Thank you so much. Cheers.